In 1861, I sat alone at my desk at King's College London and stared at a number I had not asked for. The equations had given it to me. I had been looking for electricity and magnetism. What I got back was something else entirely. I stared at that number for a long time. I checked my work. I checked it again. The number did not change. I did not understand what I was looking at. Not yet. My name is James Clerk Maxwell, and the man who made that moment possible could not do mathematics. Michael Faraday was born in 1791, 40 years before me, just south of London. His father was a blacksmith, a man who worked iron with his hands to put food on the table and did not always manage. Faraday recalled later that he had to make a single loaf of bread last him for a week, not as an anecdote, as a fact. At 14, he began as an apprentice at a bookbinder's. For 7 years, he bound books, trimmed pages, stitched spines. But when the customers were gone, he read. He taught himself chemistry. He taught himself physics. He wrote letters to scientists he had never met. At 21, he was a laboratory assistant at the Royal Institution in London. What he built there, he built alone. In the 1820s, Faraday quietly took over a room in the basement of the Royal Institution. It had been a servant's hall. It had almost no natural light. The walls were stone. The ceiling was low. He brought his instruments down there, set them on the old dumbwaiter shelves, and worked, sometimes for days at a time, with no one beside him. He kept detailed notebooks, every experiment, every result, every failure. He wrote that he had never had a student or a pupil to aid him, that he had always prepared and made his experiments with his own hands, thinking and working at the same time. In 1831, the year I was born, in that basement, Faraday moved a magnet through a coil of wire and saw that current flowed. No battery, no source, pure motion. The generator, as you know it, the dynamo, the power station, began in a former servant's hall with no windows, by a man who had taught himself everything he knew. But that was not the greatest thing he did. The greatest was something no one took seriously, something for which he was dismissed by the finest mathematicians of his time. Faraday could not do mathematics, no calculus, no algebra beyond the simplest operations, and so he did the only thing he could. He drew. He drew lines in the space around magnets, round curved lines representing fields of force. He called them field lines. He proposed that space itself, the empty space between a magnet and a piece of iron, was filled with something, a structure, a tension, something invisible that was more real than the matter surrounding it. The mathematicians of his time found this primitive. They used formulas, numbers, equations. Field lines were pictures, sketches from a man who did not speak the real language of science, decades of work, hundreds of experiments, a vision of how the world was constructed, and the people who had the tools to confirm that vision were not looking at it. Perhaps you know what that feels like, to see something clearly and have no one believe you. I was 20 when I first heard his name, 23 when I graduated from Cambridge as second in my year in mathematics, 24 when I opened his book, Faraday's Experimental Researches in Electricity, 3 volumes, published over decades, filled with observations, experiments, drawings, and his field lines everywhere. My teachers had warned me that Faraday was unmathematical, that his ideas were intuitive but not rigorous, that I should not waste my time on them. I did not listen, because as I read those pages, those pictures, those curved lines, those descriptions of force and space, I saw something my teachers did not see. I saw that Faraday was describing a structure that existed, not as a metaphor, as a reality, and that this structure, if you translated it correctly into the language of mathematics, had to yield something. In December 1855, I presented a paper to the Cambridge Philosophical Society. I was 24 years old. The title was simple: On Faraday's Lines of Force. I took Faraday's drawings and translated them, not to refute him, not to correct him, to show that what he had seen, that invisible structure,
those field lines in empty space, could be described mathematically. That his vision was not primitive, that it reached, in fact, further than even he knew. I sent him a copy. His reply reached me on March 25th, 1857. Faraday was 65 years old. He wrote that when he saw such mathematical force brought to bear on his ideas, he had at first been almost frightened, and then astonished that the subject withstood it so well. Frightened. He wrote that he was frightened. This man who had devoted his life to the invisible structure of the world, it overwhelmed him that the mathematics had proved him right. Perhaps you know that feeling too, when someone finally sees what you have known for years.
In the years that followed, my own career did not go as I had hoped. In 1856, I took a professorship in Aberdeen, in the north of Scotland. I was 25 years old, 15 years younger than any other professor in the building. I lectured 15 hours a week. I gave free evening classes to working men. I won the Adams Prize in 1859 for my mathematical proof of how Saturn's rings could remain stable. Britain's astronomer Royal called it one of the most remarkable applications of mathematics to physics he had ever seen. In 1860, the college merged with another. There was no room for two professors of natural philosophy. Despite everything, I was the one who was let go. I was 28 years old. I had just done some of the finest mathematical work of my generation, and I was redundant. I moved to London, to King's College, where a professorship had become available, and it was there, in that city, that I finally met him in person. Faraday was 69 years old when I arrived in 1860. He was frail. His memory was failing. Decades of chemical work had left their mark. He had been one of the most celebrated scientists in Britain, a man who had been offered a knighthood and turned it down, saying he preferred to remain plain Mr. Faraday to the end. But he was there, and he listened. 40 years between us. He had made his greatest discoveries in a time before I was born. And yet we sat in the same rooms of the Royal Institution, and he asked questions with a precision that shamed people half his age. I worked on, year after year. I built on his field lines. I added layer upon layer of mathematics. And in 1861, while working on a paper about the nature of electric and magnetic fields, something happened that I was not prepared for. The equations asked me to calculate the speed at which electromagnetic disturbances would travel through space. I calculated. The number was approximately 300 million meters per second. I put my pen down. I knew that number. Every physicist in Europe knew that number. It was the speed of light, a value measured through optical experiments over decades. It had nothing to do with electricity, nothing to do with magnetism, nothing to do with anything I had been working on. And yet there it was, sitting at the bottom of my calculation, unmistakable. I sat very still. The equations had not made an error. I had checked them too many times for that, which meant that the structure Faraday had drawn, those curved lines in empty space, those invisible fields around a magnet, that structure vibrated, and when it vibrated, it moved at the speed of light. Which meant one thing: light was not separate from electricity and magnetism. Light was them. Light was an electromagnetic wave, the same invisible structure Faraday had drawn in the space around his magnets. That structure was vibrating, and the vibration was light itself. I had not gone looking for light. I had followed the drawings of a man who could not do calculus, translated them into mathematics, and the mathematics had told me what light was. I sat with that for a long time. If that was true, then the equations also predicted something else, something that had never been seen, measured, or detected. Waves like light, but slower. Waves with longer wavelengths. Waves that would pass through walls, through buildings, through the entire atmosphere of the Earth. Waves that were, at that moment, completely invisible to every instrument humanity possessed. The equations were telling me they existed. The equations were telling me the world was full of something no one had ever found. I wrote it down. I could barely believe it as I wrote it. Perhaps you have had a moment like that, when something lands in front of you that you did not expect, and you sit very still because you are not sure the world is the same as it was an hour ago. In 1865, I published my complete theory, equations that united electricity, magnetism, and light in a single description of reality. Perhaps you recognize them. Then I went home. I had been unwell. I returned to my family estate in Scotland and spent 6 years working in private, writing, calculating. The theory was complete, but the world had not yet caught up with it. Most physicists found my equations too abstract, too mathematical, too far removed from anything they could see or touch. There is a particular kind of loneliness in knowing something that cannot yet be shown. Faraday had lived with it for 30 years. I had it for the rest of my life. In 1871, I returned to Cambridge as the first professor of experimental physics. I built the Cavendish Laboratory from nothing. I spent my final years overseeing the experiments of the next generation, editing the unpublished papers of scientists long dead, trying to pass on what I had learned to people young enough to take it further. In April 1879, I began to have difficulty swallowing. I continued to lecture through the end of the spring term. My students noticed that my health was failing. I gave my lectures anyway. In October, a doctor told me I had perhaps a month to live. On the 8th of October, 1879, my wife and I returned to Cambridge from our summer at home. By that point, I could barely walk. My doctor said later that no man he had ever known had met death more consciously or more calmly. I died in Cambridge on the 5th of November, 1879. I was 48 years old. The same disease had killed my mother at the same age. My equations predicted something invisible. I had not proved it. There had been no one with the equipment, the ingenuity, or the time to generate waves that no instrument could measure. 9 years after my death, in 1888, a German physicist named Heinrich Hertz stood in his laboratory in Karlsruhe. He was looking for my waves that no one had ever seen, measured, or touched. He was 31 years old. I had been dead for 9 years. Faraday had been dead for 21. He built a simple apparatus. He sent a pulse of electrical energy through it, and on the other side of the room, separated by meters of air and nothing else, no wire, no connection of any kind. A loop of wire produced a spark. Something had crossed the room. He measured its speed, 300 million meters per second. He stood in that laboratory and understood what he was holding. Not a curiosity, not an accident. The confirmation of something that had been predicted in a quiet room in London by a man who was no longer alive to hear it. Hertz said later, "This experiment proves nothing other than that Maestro Maxwell was right." But Hertz was only half correct. Maxwell had been right. And Maxwell had only been right because Faraday had drawn lines in empty space that no mathematician would take seriously. And if you are listening to this story right now, you are doing so through waves that Faraday first suspected: radio, television, the satellite signal that makes your telephone work, the transmission that puts these words on your screen. All invisible, all predicted, all begun with a man working alone in a basement with no windows, drawing lines around a magnet in a room that had once been a servant's hall. Albert Einstein kept a portrait of Faraday in his study, alongside Newton, alongside me. Einstein described my work as the most profound and most fruitful that physics had experienced since the time of Newton. But that work did not begin with me. It began with Faraday's lines. In 1861, I sat alone at my desk in London and stared at a number I had not asked for. The number was 300 million meters per second, and I knew then, even though I could not yet prove it, that Faraday's vision was right. He had no mathematics. He had drawn the world as he saw it. I had read those drawings, and somewhere in the world right now, in the walls around you, in the air between you and everyone you have ever spoken to, those invisible waves are moving. They were always there. Faraday saw them first.